was an exciting period culminating in the Les Houches Summer School in 1972, in which we solved most of the major problems in black hole theory. This was before there was any observational evidence for black holes, which shows Feynman was wrong when he said an active field has to be experimentally driven. Just as well for M-theory. The one problem that was never solved was to prove the cosmic censorship hypothesis, though a number of attempts to disprove it failed. It is fundamental to all work on black holes, so I have a strong vested interest in it being true. I therefore have a bet with Kip Thorne and John Preskill. It is difficult for me to win this bet, but quite possible to lose, simply by finding a counterexample with a naked singularity. In fact, I have already lost an earlier version of the bet, by not being careful enough about the wording. They were not amused by the t-shirt I offered in settlement. We were so successful with the classical general theory of relativity, that I was at a bit of a loose end in 1973, after the publication with George Ellis, of the large-scale structure of spacetime. My work with Penrose had shown that general relativity broke down at singularities. So the obvious next step would be to combine general relativity, the theory of the very large, with quantum theory, the theory of the very small. I had no background in quantum theory, and the singularity problem seemed too difficult for a frontal assault at that time. So as a warm-up exercise, I considered how particles and fields, which are governed by quantum theory, would behave near a black hole. In particular, I wondered, can one have atoms, in which the nucleus is a tiny primordial black hole, formed in the early universe? To answer this, I studied how quantum fields would scatter off a black hole. I was expecting that part of an incident wave would be absorbed, and the remainder scattered. But to my great surprise, I found there seemed to be emission from the black hole. At first, I thought this must be a mistake in my calculation. But what persuaded me that it was real was that the emission was exactly what was required to identify the area of the horizon with the entropy of a black hole. It is summed up in this simple formula, which contains the three fundamental constants of nature: c, the speed of light; g, Newton's constant of gravitation; and h bar, Planck's constant. I would like it to be on my tombstone. Work with Tim Hartle, Gary Gibbons, and Malcolm Perry uncovered the deep reason for this formula. General relativity can be combined with quantum theory in an elegant manner if one replaces ordinary time by imaginary time. I have tried to explain imaginary time on other occasions, with varying degrees of success. I think it is the name, imaginary, that makes it so confusing. It is easier if you accept the positivist view that a theory is just a mathematical model. In this case, the mathematical model has a minus sign whenever time appears twice. The Euclidean approach to quantum gravity, based on imaginary time, was pioneered in Cambridge. It met a lot of resistance, but is now generally accepted. The radiation from a black hole will carry away energy, so the black hole will lose mass and shrink. Eventually, it seems the black hole will evaporate completely and disappear. This raised a problem that struck at the heart of physics. My calculation showed that the radiation was exactly thermal and random, as it has to be, if the area of the horizon is to be the entropy of the black hole. So how could the radiation left over carry all the information about what made the black hole? But if information is lost, this is incompatible with quantum mechanics. This paradox had been argued for 30 years, without much progress, until I found what I think is its resolution. Information is not lost, but it is not returned in a useful way. It is like burning an encyclopedia. Information is not lost, but it is very hard to read. In fact, Kip Thorne and I had a bet with John Briskill on the information paradox. I gave John a baseball encyclopedia. Maybe I should have just given him the ashes. Between 1970 and 1980, I worked mainly on black holes and the Euclidean approach to quantum gravity. But the suggestions that the early universe had gone through a period of inflationary expansion renewed my interest in cosmology. Euclidean methods were the obvious way to describe fluctuations and phase transitions in an inflationary universe. We held an field workshop in Cambridge in 1982, attended by all the major players in the field. At this meeting, we established most of our present picture of inflation, including the all-important density fluctuations, which give rise to galaxy formation, and so to our existence. This was 10 years before fluctuations in the microwave were observed, so again in gravity, theory was ahead of experiment. The scenario for inflation in 1982 was that the universe began with a Big Bang singularity. As the universe expanded, it was supposed somehow to get into an inflationary state. I thought this was unsatisfactory, because all equations would break down at a singularity. But unless one knew what came out of the initial singularity, one could not calculate how the universe would develop. Cosmology would not have any predictive power. After the workshop in Cambridge, I spent the summer at the Institute of Theoretical Physics, Santa Barbara, which had just been set up. We stayed in student houses, and I drove into the institute in a rented electric wheelchair. I remember my younger son, Tim, age 3, watching the sunset on the mountains, and saying, "It's a big country." While in Santa Barbara, I talked to Jim Hartle about how to apply the Euclidean approach to cosmology.